There are no simple answers to the questions posed regarding heat buildup in conduit duct banks. Firstly, NEC Article 310 does not contain any specific guidelines relative to heat buildup in conduit, and therefore the ampacity adjustment factors of Table 310.16 are not applicable. Secondly, IEEE Standard 835-1994 provides some information relative to the adjustment of ampacity for multiple cables in a duct bank. However, this information is not readily usable and is based on many assumptions. In this standard, the multi-conductor adjustment factor is for use with the ampacity tables of Chapter 9 of the standard. When used in conjunction with Article 310, these factors can be used, but they must be adjusted to reflect the relationship of the NEC tables to the IEEE standard tables. Thirdly, there are software packages and consultants that specialize in determining the ampacity ratings for cables and raceways. However, their accuracy is very dependent on the input of the actual conditions. In general, the ampacity calculation programs do not consider effects such as the ambient temperature and the duration of the load current. Fourthly, the type of concrete slurry that is being proposed may not have any thermal conductivity. Therefore, its use may not be a significant factor in reducing the heating effects in the duct bank. Fifthly, the best solution is to have a system design that maintains the ampacity of the cables in the duct bank at values greater than the load current. This can be achieved by using more raceways, larger conductors, or by operating at lower voltage. Let's delve deeper into each of these points to provide a more comprehensive understanding. Regarding the NEC, while Article 310 provides ampacity tables for conductors, these tables assume specific conditions, such as a limited number of conductors in a raceway or direct burial, and a specific ambient temperature. When these conditions are not met, the NEC requires ampacity adjustment factors to be applied. These factors account for things like ambient temperature exceeding 30 degrees Celsius or more than 3 current carrying conductors in a raceway. However, the NEC doesn't offer specific guidance on rating for a large duct bank with multiple conduits in close proximity. This is because the heat dissipation characteristics of such a system are complex and depend on numerous factors. Moving on to IEEE Standard 835-1994, this standard, titled IEEE Recommended Practice for Power Cable Ampacity Determination, provides more detailed guidance on calculating ampacity for cables installed in various configurations, including duct banks. It uses thermal circuit models to estimate cable temperatures and, consequently, ampacity. The standard considers factors such as cable size, insulation type, burial depth, soil thermal resistivity, ambient temperature, and the number and configuration of cables in the duct bank. However, as mentioned, using this standard effectively requires careful consideration of the assumptions it makes and adjusting the results to align with the NEC. The multi-conductor adjustment factor referred to in the standard is applied to the base ampacity values found in the IEEE tables. These tables are based on specific assumptions about cable construction and operating conditions. Therefore, when applying these factors to NEC ampacity tables, which may have different underlying assumptions, adjustments are necessary to ensure accurate results. It's important to note that the IEEE standard involves complex calculations and requires a good understanding of heat transfer principles. It's often necessary to use specialized software or consult with experts to perform these calculations accurately. Speaking of software and consultants, several specialized tools and services can assist in determining ampacity ratings for cables in raceways. These tools typically use sophisticated algorithms to model heat transfer in the system, taking into account factors like cable size, spacing, burial depth, soil thermal resistivity, ambient temperature, and load current. However, the accuracy of these tools depends heavily on the quality of the input data. It's crucial to accurately model the actual conditions of the installation, including the soil thermal resistivity, ambient temperature, and load profile. Furthermore, many ampacity calculation programs don't fully account for factors like ambient temperature variations or the duration of the load current. For example, If the ambient temperature is consistently lower than the design temperature, the actual ampacity of the cables may be higher than calculated. Similarly, if the load current is intermittent or cyclical, the cables may have time to cool down between periods of high current, further increasing their effective ampacity. Therefore, it's important to carefully evaluate the assumptions and limitations of any ampacity calculation tool and to consider these factors when interpreting the results. Regarding the use of concrete slurry, the thermal conductivity of the slurry is a critical factor in determining its impact on heat dissipation. If the slurry has low thermal conductivity, it may actually act as an insulator, trapping heat within the duct bank and increasing cable temperatures. In this case, using the slurry would be counterproductive. On the other hand, if the slurry has high thermal conductivity, it can help to dissipate heat away from the cables, reducing cable temperatures and increasing ampacity. However, even with high thermal conductivity, the slurry's effectiveness depends on its ability to conduct heat away from the duct bank. If the surrounding soil has low thermal conductivity, the heat may not be able to dissipate effectively, limiting the slurry's benefit. Therefore, it's essential to consider the thermal properties of both the slurry and the surrounding soil when evaluating the use of concrete slurry in a duct bank. Ultimately, the best approach is to design the system to ensure that the ampacity of the cables in the duct bank is always greater than the load current. This can be achieved through several strategies. Firstly, increasing the number of raceways can reduce the number of conductors in each raceway, thereby reducing the heat generated in each raceway. Secondly, using larger conductors can increase the ampacity of each conductor, allowing for a higher load current without exceeding the conductor's temperature rating. Thirdly, operating at a lower voltage can reduce the current required to deliver the same amount of power, thereby reducing the heat generated in the cables. In addition to these strategies, it's also important to consider the overall system design and to ensure that the duct bank is properly ventilated and protected from direct sunlight. Proper ventilation can help to dissipate heat away from the cables, while protection from direct sunlight can reduce the ambient temperature around the duct bank. In conclusion, addressing heat buildup in conduit duct banks requires a comprehensive approach that considers various factors, including the NEC IEEE standards, specialized software, and the thermal properties of the surrounding materials. By carefully evaluating these factors and implementing appropriate design strategies, it's possible to ensure that the cables in the duct bank operate within their ampacity ratings and that the electrical system is safe and reliable. It is crucial to conduct a thorough engineering analysis, considering all relevant factors and using appropriate tools and techniques to determine the optimal design for the specific installation. The ampacity of conductors is a critical parameter in electrical system design, ensuring safe and reliable operation. When multiple conductors are installed in close proximity, such as in a duct bank, the heat generated by each conductor can affect the temperature and, consequently, the ampacity of the other conductors. This phenomenon, known as mutual heating or thermal diarrheting, must be carefully considered to prevent overloading and potential failures. The NEC provides ampacity tables based on specific conditions, such as the number of conductors in a raceway and the ambient temperature. However, these tables are often insufficient for complex installations like duct banks, where the thermal interactions between conductors are more pronounced. In such cases, more sophisticated methods are needed to accurately determine the ampacity of the conductors. IEEE Standard 835 offers a more detailed approach to ampacity calculations, considering factors such as cable size, insulation type, burial depth, soil thermal resistivity, and the number and configuration of cables in the duct bank. The standard uses thermal circuit models to estimate cable temperatures and, consequently, ampacity. These models represent the heat flow path from the conductors to the surrounding environment, taking into account the thermal resistances of various materials such as the cable insulation, the conduit, the soil, and the air. By solving these thermal circuit models, it is possible to determine the temperature of each conductor and compare it to its maximum allowable temperature. If the conductor temperature exceeds the maximum allowable temperature, the conductor is considered overloaded, and its ampacity must be reduced. The multiconductor adjustment factor in IEEE Standard 835 accounts for the mutual heating effect of multiple conductors in close proximity. This factor reduces the ampacity of each conductor based on the number of other conductors in the duct bank and their spacing. The closer the conductors are to each other, the greater the mutual heating effect and the lower the ampacity of each conductor. In addition to the mutual heating effect, other factors can also affect the ampacity of conductors in a duct bank. These factors include the ambient temperature, the soil thermal resistivity, and the presence of other heat sources or sinks. The ambient temperature is the temperature of the surrounding air or soil. Higher ambient temperatures reduce the ampacity of conductors because they reduce the temperature difference between the conductor and its surroundings, making it more difficult for the conductor to dissipate heat. The soil thermal resistivity is a measure of how well the soil conducts heat. Higher soil thermal resistivity reduces the ampacity of conductors because it makes it more difficult for the heat to dissipate from the duct bank to the surrounding soil. The presence of other heat sources or sinks can also affect the ampacity of conductors. For example, if there are other underground cables or pipes nearby, they can either add heat or remove heat from the duct bank, affecting the temperature of the conductors. To accurately determine the ampacity of conductors in a duct bank, it is necessary to consider all of these factors. This can be done using specialized software or by consulting with experienced electrical engineers. Specialized software can perform complex thermal calculations to estimate cable temperatures and ampacity based on various input parameters. These programs typically use finite element analysis or other numerical methods to solve the thermal circuit models. Consulting with experienced electrical engineers can provide valuable insights and guidance on the design and installation of duct banks. The electrical engineers can help to identify potential problems and develop solutions to ensure that the ampacity of the conductors is adequate for the intended load. One of the key considerations in duct bank design is the spacing between conduits. Closer spacing results in greater mutual heating effects and lower ampacity. However, closer spacing also reduces the overall size of the duct bank and can be more economical. Therefore, it is necessary to strike a balance between these competing factors. Another consideration is the type of conduit used. Different types of conduit have different thermal conductivities. For example, PVC conduit has a lower thermal conductivity than steel conduit. Therefore, using steel conduit can help to dissipate heat more effectively and increase the ampacity of the conductors. The type of backfill material used around the duct bank can also affect the ampacity of the conductors. Backfill material with high thermal conductivity can help to dissipate heat more effectively, while backfill material with low thermal conductivity can trap heat and reduce ampacity. It is important to use backfill material that is specifically designed for underground electrical installations. The depth of burial of the duct bank can also affect the ampacity of the conductors. Deeper burial depths result in lower ambient temperatures and can increase ampacity. However, deeper burial depths also increase the cost of installation. Therefore, it is necessary to strike a balance between these competing factors. In addition to these design considerations, it is also important to properly install and maintain the duct bank. Improper installation can lead to reduced ampacity and potential failures. Regular maintenance can help to identify and correct any problems before they become serious. One of the most common problems in duct banks is water intrusion. Water can reduce the insulation resistance of the conductors and lead to short circuits. It is important to ensure that the duct bank is properly sealed to prevent water from entering. Another common problem is cable damage. Cables can be damaged by rodents, digging, or other activities. It is important to protect the cables from damage and to repair any damage promptly. By carefully considering all of these factors, it is possible to design, install, and maintain duct banks that provide safe and reliable power distribution. The design and installation of a duct bank system for a large commercial project with multiple 3000 amp services, as described in the original prompt, presents a significant engineering challenge. The large number of conduits, the high current levels, and the potential for heat buildup necessitate a thorough analysis and careful consideration of various factors to ensure safe and reliable operation. The initial concern regarding heat dissipation is valid, and the absence of specific guidelines in NEC Article 310 for such complex scenarios highlights the need for a more in-depth evaluation. While NEC Article 310 provides ampacity tables and adjustment factors for various conditions, it does not adequately address the thermal interactions within a large duct bank with closely spaced conduits carrying high currents. The ampacity adjustment factors in Table 310.16, which account for the number of current-carrying conductors in a raceway at ambient temperature, are insufficient to accurately determine the ampacity of conductors in a dense duct bank configuration. IEEE Standard 835 offers a more comprehensive approach to ampacity calculations for cables in underground duct banks. This standard utilizes thermal circuit models to estimate cable temperatures based on various factors, including cable size, insulation type, burial depth, soil thermal resistivity, ambient temperature, and the number and configuration of cables in the duct bank. The thermal circuit model represents the heat flow paths from the conductors to the surrounding environment, considering the thermal resistances of the cable insulation, conduit, soil, and air. By solving this model, the temperature of each conductor can be determined and compared to its maximum allowable temperature. The multi-conductor adjustment factor in IEEE Standard 835 accounts for the mutual heating effect of multiple conductors in close proximity. This factor reduces the ampacity of each conductor based on the number of other conductors in the duct bank and their spacing. The closer the conductors are to each other, the greater the mutual heating effect and the lower the ampacity of each conductor. However, even with IEEE Standard 835, the accuracy of the ampacity calculations depends heavily on the accuracy of the input data. The soil thermal resistivity, ambient temperature, and load profile must be accurately determined to obtain reliable results. Soil thermal resistivity can vary significantly depending on the soil type, moisture content, and compaction. Ambient temperature can also vary depending on the location, time of year, and depth of burial. The load profile, which represents the variation of current over time, is also crucial for accurate ampacity calculations. If the load is intermittent or cyclical, the cables may have time to cool down between periods of high current, increasing their effective ampacity. Specialized software packages and consultants are available to assist in performing ampacity calculations for complex duct bank configurations. These tools typically use finite element analysis or the numerical methods to solve the thermal circuit models. They can also account for factors such as ambient temperature variations, load profiles, and the presence of other heat sources or sinks. The proposal to encase the conduits in concrete slurry raises concerns about its potential impact on heat dissipation. The thermal conductivity of the concrete slurry is a critical factor. If the slurry has low thermal conductivity, it may act as an insulator, trapping heat within the duct bank and increasing cable temperatures. In this case, the use of the slurry would be detrimental. On the other hand, if the slurry has high thermal conductivity, it can help to dissipate heat away from the cables, reducing cable temperatures and increasing ampacity. However, even with high thermal conductivity, the slurry's effectiveness depends on its ability to conduct heat away from the duct bank. If the surrounding soil has low thermal conductivity, the heat may not be able to dissipate effectively, limiting the slurry's benefit. Therefore, it is essential to consider the thermal properties of both the slurry and the surrounding soil when evaluating the use of concrete slurry in a duct bank. An alternative approach to encasing the conduits in concrete slurry is to individually form the banks. This would allow for better air circulation around the conduits, which can help to dissipate heat. However, it would also increase the overall size of the duct bank and may be more costly. The best solution is to design the system to ensure that the ampacity of the cables in the duct bank is always greater than the load current. This can be achieved through several strategies. Firstly, increasing the number of raceways can reduce the number of conductors in each raceway, thereby reducing the heat generated in each raceway. Secondly, using larger conductors can increase the ampacity of each conductor, allowing for a higher load current without exceeding the conductor's temperature rating. Thirdly, operating at a lower voltage can reduce the current required to deliver the same amount of power, thereby reducing the heat generated in the cables. In the specific case described, the duct bank consists of 5 groups of conduits with 24-inch spacing between groups and 18-inch cover. Bank 1 contains 4 4-inch conduits with 4 750 kc mil conductors and 1 #4/0 ground. Bank 3 contains 3 4-inch conduits with 4 500 kc mil conductors and 1 #2/0 ground, plus 1 4-inch spare conduit. Bank 4 is identical to Bank 3. Bank 5 contains 1 4-inch conduit and 1 1/2-inch conduit with a known wire size. The distance from the service entrance section to the electrical room is 500 feet. Given the high current levels 1400 amps in Bank 1, 1000 amps in Banks 3 and 4, and 600 amps in Bank 5, and the close proximity of the conduits, heat buildup and ampacity dating are significant concerns. A thorough engineering analysis is necessary to determine the ampacity of the conductors in each conduit, taking into account the mutual heating effects and the thermal properties of the surrounding materials. The analysis should also consider the load profile and ambient temperature variations. Based on the results of the analysis, appropriate measures can be taken to mitigate heat buildup and ensure that the conductors operate within their ampacity ratings. These measures may include increasing the number of raceways, using larger conductors, operating at a lower voltage, improving ventilation, or using a concrete slurry with high thermal conductivity. In addition to the electrical considerations, it is also important to consider the structural integrity of the duct bank. The duct bank must be able to withstand the weight of the soil and any other loads that may be imposed on it. The conduits must also be protected from damage due to digging or other activities. Proper design and installation are essential to ensure the long-term reliability of the duct bank.